शशिकांत सर. Shaila ma'am.
Yes, ma'am.
Sir has joined, no?
Yes, SK. Yes, ma'am.
Sir, Shashikant sir.
I think he has leave. No, ma'am.
He's there.
Is there?
Yeah, are you able to hear me?
Yes, sir.
Okay.
Good evening, sir.
Yeah, good evening. So how we start?
Sir, we will start. Just wait.
Okay, ma'am. Yeah.
A very warm and pleasant evening to one and all present here. We welcome you to our ninth session of 6 days online ATAL FDP, that is Quantum Computer System Organization in Ethics and Security in Data-Driven Quantum Computing. I, Mrs. Shaila Pawar, on behalf of the Information Technology Department at AC Patil College of Engineering, Kharghar, welcomes Dr. Shashikant Pandey to the ATAL FDP on next-gen computing, advances in HPC, and quantum technologies for data-driven insights. Without further ado, allow me to introduce today's speaker, Dr. Shashikant Pandey. Dr. Shashikant Pandey is scientist at Society for Electronic Transaction and Security, Chennai, PhD from University of Delhi, and Master of Science from Banaras Hindu University. His research focuses on cryptographic Boolean functions, quantum resistant cryptography, and privacy preserving technology. We welcome you, sir. Please accept our virtual token of respect.
Yeah, thank you, ma'am.
Now I request Dr. Shashikant Pandey, sir, to start the session. Over to you, sir.
Yeah, thanks for the introduction, ma'am. I'm just sharing my slide. Just let me know you all are able to see it or not.
Yes, sir, it is visible.
Yeah. So, okay, so I can start now. Okay, are you able to see it? Yeah.
Yes, sir.
Yes,
Okay.
yes, sir.
Yeah. So, as you mentioned, I belongs to Society for Electronic Transaction Security. This is a government-funded autonomous body working especially in cyber security. So, uh, what I will cover in this talk is basically how quantum resistance is our cyberspace, and what type of, mm, since the topic of this FDP is next generation computing, so I will just briefly discuss that how this is going to be in the domain of quantum field, and in terms of quantum cryptography, as well as in terms of post quantum enable security in our cyberspace. So, uh, briefly, I'll tell you then the major objective for next generation computing is basically how you process fastly the information. It means how you process the data with more efficient way. So the second aspect is, I can say that energy efficiency on your processing, because I can tell you, like, if you see the development in quantum computing as well as other aspect of computing, then the question is raising day by day, like how efficient those computing are in terms of energy efficiency. It means ultimately the energy is the basic requirement for all those computation tasks. So this is the prime question, and I can say this is a futuristic question also. And third one, that whatever the task you are going to do on classical computer, so how optimally you can perform those tasks using those next generation computing. So majorly, if you think that how what type of verticals has been raised till date in next generation computing, then we can categorize those things in these three different vertical. First one is quantum computing. Next one, you can say that they are emerging technique, neuromorphic computing and photonic computing. In fact, I can say since last 10 years that quantum computing development has been grown in that level where you can see the implementation as well as the effect of those computing, in fact specifically in quantum computing, in all aspects of our cyberspace. Remaining two are in emerging phase, so their effect, how they will affect our present cyberspace, we can't picturize clearly. But in terms of the effect of quantum computing, you can see those changes. In fact, these, I can say, if you say that this last 5 year or next coming 5 year, or till 2030 or 35, I will show you those yeah, evidence of reports also, where you can see that till 2035 what are going to be changed because of this quantum computing development. So more or less, if we see that what type of enhancement we are achieving in terms of quantum computing, then this graph is the answer for that question. Like if you see that, I already told like how your problem is going to be solved on the enhanced computational power like quantum computer. So the graph will represent that the effect of those power of different quantum computers. So if you see here, then you can easily see that the
Sir,
horizontal. Yeah.
sir, can you please present your screen in full screen mode?
Oh, you are not able to see.
Your screen is visible, but not in full screen mode.
Okay, just wait. Now I think, are you able to see my whole screen?
Yes, sir.
But let me try once more. Yeah, now this is fine.
Yes, sir. Yes, sir. Thank you. Thank you, sir.
Yeah, yeah. Okay, so basically, I was here and I was telling you this graph is actually, you can see the vertical line is actually the time, and the horizontal line is the size of your problem. So at initial, it means if for a smaller size of problem, here it will represent n. It means you can refer it as that, suppose you're trying to solve an n variable equations, then the size of the problem will come out to be n. This n refer a rough way of the size of the problem, but I just quote one example. So if you see this, then you can find that for a smaller size of the problem, the classical computer has the advantage. But for bigger size of the problem, quantum computer is showing, from this line it is showing a total gap between the time, for the performance, for your problem. So actually, uh, it is happening in all those framed problem, in terms of if someone is trying for simulation on different platform of quantum computers, qskit and all those, then they can easily verify these things, that how things are happening. So this to the motive to show this graph is actually, if we think about those problem which has large size, then in that case the quantum computer is showing very much advantage in terms of getting the solution. So the question is coming from there is like, since based on size, this quantum computer is showing the advantage, and almost, if I can say that, our the communication protocols, or the security of our cyberspace relies on those things where the time is playing a key role. Means, if you are not able to solve this problem in this much time, then you are relying that this is the safe phenomena to start communication. So this is, if this is the foundational thing in our communication system, in the cyberspace, the why what I am referring for communication system in cyberspace, it means what type of protocols or what type of algorithms we are using, which are saying that our communication is safe or not. So those relies on those, on some hard problem, where the size of the problem is designed in such a way so that our classical computer is not able to solve it. So if this graph is going to be in such a way, then the size is not going to an issue if quantum computer has been developed. So that's why this problem is raising on, like, how safe is our communication if quantum computer will come. And it is obvious, like, uh, to building quantum computer is not that much cheap task, so that I can say that you or me or some common people can afford a quantum computer. So the meaning is very simple, like quantum computer is needs so many investment. So in that case, the reliability on those people or those big chunks who are actually in the field of quantum computer is a question mark for us also, like how safe our communication if these big chunks are going to developing these quantum computers. So uh, if we trying to find out the answer for that what type of security on which we are relying on cyberspace, so some key factors are there. So I will highlight that what type of key factors are there and how the strength is going to be developed on those key factors, so that the our public communication infrastructure is going to be safeguarded and in terms of the quantum threats. So I will just briefly introduce those things, like but majorly I will show you that how this post quantum communication or post quantum cryptography is going on and where it is heading towards in terms of development of quantum computers. So the basic bold points are the cryptography. It is the core part of the communication system. Quantum computing. So it is going to be in terms of development of solving those hard problems on which our communication system has been relied. Post quantum cryptography is just came after the threat of those algorithm which has been given by some very famous people in quantum computing, like using those algorithm you are able to solve those problems on which our current communication system is relying. So if we see that the picture of the cryptography in terms of industrial perspective, then you can divide those cryptographic development in three categories. First one is the symmetric cryptography, where you are using same key to encrypt and decrypt, and another one is asymmetric cryptography, where you are using um, some one key for encryption and another key for decryption. And another one is a hash function. Why I put it in a different vertical? Because this is a building blocks, and most of our communication protocols relies on the design of hash function and their security. Here you can see the examples of symmetric ciphers and asymmetric ciphers. So RSA and ECC are well known and very common in public key encryption techniques on which we are relying our current cyberspace. So and they are based on actually those hard problem which are not safe from quantum threats. So what would look the post quantum scenario of the cryptography? It means here the meaning of the post quantum is that um, this keyword has been raised by an agency. You can say that the agency is available in US, NIST. If you or if anyone has in background in cyberspace, then they knew it, that what NIST is doing. So basically, the post quantum cryptography has just came, you can say that after before 10 years. So NIST has started to a call for those communication algorithms which will safeguard our communication, our cyberspace in terms of quantum threats. So, in fact, the NIST is doing in terms of all those aspects of cyberspace. So here, the picture came in 2016 or 18, when NIST has initiated the call for public key encryption algorithms, and around the globe they have they received, I think, I will show you that statistics also, that how many algorithms they have received, and what actually the state what actually the stage is now. So if I'm going to this slide, then you can briefly divide the post quantum cryptography in these three verticals. First one is quantum computing. It means whatever is happening in computational aspect of coming from the quantum technology. So you can frame these three algorithms. There are other algorithms also uh, proposed by scientists for on quantum computer. So these three algorithms are well-known algorithms: Shor algorithms, Grover's algorithm, this HHL algorithm. So the Grover's algorithm is basically a search algorithm. Since search is itself difficult in classical computer, so Grover's proposed algorithms which will search in unstructured database, and it shows that it will give the result in polynomial time. Similarly, in the same fashion, Shor has given algorithms to factorize a given number. So, factorization is related to the algorithm RSA, which I earlier briefed. Like RSA is actually rely on the problem of the factorization. So, Shor has proposed algorithms, and this is the you can say that ultimate threat started. Like if someone has the that much efficient quantum computer, then they can break the our public key crypto system, which is based on RSA. And this HHL algorithm is basically a solution of linear equation. So how this linear equation is playing a role in nowadays cryptography, I will brief later. Another vertical is the hard problem. It means the why I added this hard problem here, because I told you that NIST has initiated this the call for a post quantum cryptographic algorithm submissions, and finally they land on two. It means now the state is that they finalize these two algorithms, dilithium and kyber. They are the name of those algorithms. Dilithium for digital signatures. It means if you are going to sign digitally, then you have to use this algorithm for post quantum safety. And kyber is for key encapsulation mechanism. It means if you are going to share a key between two communication party, then you will use kyber for your post quantum safety. So but what is common between these two is that both of these algorithms relies on a hard problem which is named as LWE. It means learning with error. So I will brief this what is the problem this is, but the common thing is that. So that's why this vertical is very much important, like to find out some more algorithms on different hard problem, because they have a common. So how you rely on a single hard problem, and you can say that our communication system is secure. I will brief you that this the meaning of those hard problem in terms of our available communication in classical terms. Then how what is the difference among them? And last vertical is the QKD. QKD is quantum key distribution. It means it is completely based on the quantum physics technology. So you are relying on the inherent randomness of quantum nature, and using that you are able to develop a protocol which will share a common key between two parties. So this BB84 is the name of that protocol. So using this protocol, you are able to share a common key between two parties. So this has proposed in 1984, and this that's why this BB84 is there. And BB word is coming from the name of those proposer. And actually, I think last 2 year before they got the Nobel Prize. So there are some other protocols also in QKD. I just added this one. So because this is common protocols around the globe, people are using for development of QKD. Now, if you see the overall picture of the quantum technology, how it is going on, then you can divide those things in these three categories. First one is the quantum computing, another one is the quantum communication, and third one is the quantum sensing. So if you find out the place of the QKD, then it will come under quantum communication, because the 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 the, the application for that QKD is to communicate. So similarly, if you see the quantum sensing, then the quantum clock, it means, is one of the product of that quantum sensing technology. Similarly, in case of quantum computing, so there are so many quantum computers proposed by different agencies. So it is the third vertical. Now, if you see I just added these two in this slide, and next slide I will show you that how those quantum technology is going to affect uh, uh, the different vertical of problems and areas. So this is taken from that report, and that report is telling like this black circle is actually representing that disruptive impact. It means on which sector the the development in quantum computing will affect, uh, in which sense. So if you see the factorization, I already told, like, factorization is basically breaking the RSA encryption. So if you see that financial sector, it will show a disruptive impact. Similarly, the optimization problem using those quantum technology will affect finance sector very much. Similarly, in life science. Similarly, in this TTL is showing that travel, transport, and logistics. So, and sampling and search in case of finance, quantum machine learning and AI. So an optimization will also affect this TTL. So there are just not a single area in terms of, just I can say that the cyberspace is having the problem, or you can say effective domain, where the quantum technology is going to be effective. It is just changing all those aspects in all those sectors. So another interesting statistics you can see is that, and this is taken from the same report from the McKinsey, like whatever the patent filed by those technology in quantum area and their statistics. So you can see that the purpose to do the patenting is, the one of the major purpose is the commercial part. So if you see that the most of the patent in all those vertical of quantum technology, quantum communication, and quantum sensing are taken by China, Japan, and those. So that is also a figure where we all have to look at how those things in quantum technology is going on. Now, I already told like how things is happening in the classical technology of communication. Then we relying on the problem of factorization, which is actually the core part of the RSA algorithms. Similarly, the discrete logarithm problem we are using for elliptic curve, and this elliptic curve is useful in our digital signature for classical communication. And hash function, I already told, some code based cryptography already is there. So these major verticals are there in pre-quantum technology for communication in terms of cryptography. And if you go to the detail of that factorization problem, then simply I can say that suppose you have this n and you have to factorize, you have to find two prime number which will divide this. So for that itself, Shor has proposed that algorithm that you are able to factorize a big number in polynomial time. So RSA is actually based on the problem of factorization. So this is just a simple example, like how the private key and public key has been generated in RSA using two prime numbers, and then you are able to start a communication uh, uh, safely. But since the factorization itself under threat because of quantum computer, so it is there to remove those things to safeguard our communication. If you talk about another hard problem, then this is the called discrete logarithm problem, on which our key sharing mechanism has been uh, developed. So if if in a simple term I can say that you have three equations and you have to find the value of x for these three equations. So this is called discrete log problem. And how we sharing those keys between Alice and Bob, and it is relies on the problem of discrete log. So this is the example, like this one, Alice and Bob want to share a secret key, or they want to generate a common key to start communication. Then they start with these. Alice have these generated three numbers, Bob have generated this number, and Alice sends this G, P, and A. A is coming to be G to the power A mod P, and similarly. So I'm not going to details of those things, but I'm telling that the purpose to add this is to highlight those hard problems on which our current communication system is relying. And this quantum computing is there are algorithms which are claiming that if you have this much number of qubits, then you are able to break those systems. So yeah, so the question will simply the question will come like how many qubits required to solve those. So this is again a very far from the present scenario, but this we are talking about on those evidence which is available in public. So we don't know. It means it. In fact, it means like we have to prepare for those also where which information is not available. So if you see that the RSA algorithm, then here the meaning of RSA 2048 means the size of the key is 2048 bit. So this level of it simply I can say that how the longer your key is, the longer your security. But they have a threshold also, because if you are increasing the size of the key, then you are losing the efficiency and all those. So here the picture for the RSA 2048 key, 2048 bit key. So it needs to running Shor algorithm to break those RSA, you need 20 million qubits, and it will run till 8 hours your algorithm. Then you are able to break this. Similarly, here for AES 256, AES is also a very famous encryption algorithm where 256 means that the size of the key, 256 bit. So for that, you are applying Grover's algorithm. It is taken from some referred paper. So these are available in reference. I will show you. So 1500 qubits are required to perform this much reversible S box operation to break this AES. So The meaning of it is not in terms of time, it is in terms of S box, because S box is a very fundamental building block of designing AES. So this much computation you have to perform on S box on this much qubits, then you are able to break the AES 256 bit encryption. So yeah, so now this was a picture of uh, the pre-quantum, you can say, in just a rough language. But what is happening in post-quantum technology? So since I told that NIST has been started this thing in 2018, parallelly to NIST, in fact, other government also initiated the call to find out those algorithm which will safeguard our communication. So South Korea has initiated 2023. China has started in 2018. So parallelly, they have initiated. The people have submitted their algorithms, and finally they reached at those state. In fact, in 2023 itself, last year, last year itself, NIST has finalized those algorithms. In this slide, you can see that what is the plan for the Korean government to shift the available classical communication for the post-quantum safe communication system. So this has been taken in 3 years before from a document of Korean government. But recently, NIST has published a, a document for the migration of the current communication system to post quantum communication system. And this is not happening in just document, this is happening in practical also. Last 1 year before itself, they have 2 years before itself, they have started the migration of the current communication system to post quantum. It means whatever the finalized algorithm they have, they are going to enable in our available communication system. Recently, Google has enabled those. I told you the Kyber key encapsulation, key sharing mechanism. So Google has enabled this Kyber in their browsing, the browser. If you see, then you are able to see that it is under trial mode. So but they have started to shift those encryption standard from pre-quantum to post-quantum. So here these tables are clearly available in those documents. From those documents itself, I have taken, like, this ECDSA is digital signature algorithm based on elliptic curve. This FIPS 186 minute, it means they are the standards. So if you are using these algorithm for digital signature algorithm of 112-bit key security, then it is not allowed after 2035 based on the recommended document of the NIST. It means they are measuring the threads according to the time, and they are telling, like, we have to shift, we have to move towards the new standard algorithms. Similarly, they were telling for RSA also, if you are using RSA of 112-bit key security, then till 2035 you have to move towards the post quantum algorithm, which are safer in terms of quantum threats. Similarly, this was for digital signatures. This is for key establishing. So I already told, like, there are two common categorization in cyberspace. One is how you digitally sign, and another one is how you share a common key. So how you digitally sign, so actually they relies on these algorithms. How you share a common key, so they relies on mostly these algorithms. But for these much, but the key may vary. So some of devices are using different size of keys, some of devices are using different size of key. So based on the survey of those things, they find out that if you are using these much bit key for the securing of key establishment scheme, then till 2035 you have to not use directly. Either you have to increase the size of the key or go to those algorithms which are quantum safe. Now this I told you, like, all these agencies around the globe is looking for those algorithms which are quantum safe. So US has started, China has started, Russia has started, and they are just, it is so it is just to highlight you, like, all of them are not relying on just LWE hard problem. They are going for some other standards also. So the question is, like, what are the hard problems and how you categorize those submissions in the algorithms. So there are uh, verticals in cryptography. Based on those verticals based on the hardness of the problem, and those submissions came in different verticals. If we say that this is first category is the lattice based cryptography, then there were two submissions on lattice based cryptography. No, sorry, more than two submission, but two has been finalized. So crystal kyber and crystal dilithium, they are the name of the algorithm which has been finalized under this category. Similarly, another vertical is multivariate cryptography. Here, one submission where I'm talking about NIST, whatever happened in the NIST call. So the rainbow is one of the algorithm for digital signatures, and they finalized, they reviewed it in all those stages in this category. Another one is hash based cryptography. So Sphinx Flux is another digital signature algorithm which is based on the hash based cryptography. Another vertical is code based cryptography. So the NTRU is algorithm which has been submitted under this category. The last one is the interesting, like super singular elliptic curve isogeny cryptography. In that category, this Psych and Sid two algorithm has been proposed. So see, 2016 to 18 the call were there, and these two algorithm has been submitted for that. They passed initial evaluation, they came in, and you will become surprised to know in the year 2022 21 these two algorithm has been broken. It means still that all the evaluation is going on, and you can see that they evaluated and they were telling that it is post quantum safe. That the and we followed to the next step and next step, and finally in 2022, a very famous paper is there also, where they have shown, like, just using a simple laptop they are able to break those two digital signature algorithms in just 1 hour. So it means, and if you go to their website, then you can find a complete disclaimer for these two algorithms, and they intentionally kept those documents on this website so that people will aware that, okay, so it is not like it has been going to pass all those things, then we are telling that they are safe for quantum safety. So because of, and they especially mention in that website itself that uh, uh, since we have participated there and we have broken, but this broken itself will create an awareness, then we are here. So that was interesting. If we talk about other submissions in different countries, then you can see that China has listed this two algorithm. They have finalized this AIGI sign. In case of NIST, 82 algorithm received around the globe first. So see what is the figure also. Like there are not that much heavy amount of algorithm they find out and they are going to shortlisting, but it is just a limited number of algorithms, and among that they are going to shortlisting the post quantum safe algorithms. Finalists are Kyber and dilithium. Now the question is that what we are talking the hard problem. So in terms of hard problem, since both of these two algorithms are based on LWE, which is lattice based, and in fact this is a one of the reason. So NIST is still open for reviewing of the new algorithms, and they're still on for the next level review of the submitted algorithm, because the reason is that we rely on the single hard problem for digital signature as well as key encapsulation. If both of them are relying on same hard problem, and sometimes someone will propose an algorithm to break those hard problems, then both of the infrastructure will hamper. So they are still on and they are looking for the submission for different vertical of hard problem. Now what is the actually LWE problem, and what is the lattice based cryptography? So lattice based cryptography is basically developed on the well known mathematical structure which is called lattice. So the meaning of lattice is, I can say in such a way, like if you have n number of linearly independent vectors and you sum all of those vectors with integer multiple, then this will form a lattice. So this is the simple example, simple definition of a lattice. Now in this structure, so this definition create a structure where the elements are there. So in this structure, two problems are hard. First one is the shortest vector problem, another one is the closest vector problem. The simple meaning of the shortest vector, it means what will be the shortest vector in this lattice, and closest vector problem is that if you have a vector in this lattice, then find out the another vector which is closest to that one. So finding those, the solution for these two problem is computationally hard. So yeah, actually if you frame the definition of those things, then we can frame it this way. But I already mentioned that what is the meaning of the shortest vector and what is the meaning of the closest vector problem. Now if we come to the development of this LWE problem, then this LWE problem has been built on this shortest vector problem and closest vector problem. This problem has been proposed by Oded Reggio. So he is very well-known mathematician, and he proposed those things in 2005. Later on, the development of algorithm has been built on this LWE problem. Now the question is that how this LWE problem has been framed on lattice. So in a simple way, if you are going to sample a matrix A, and if you are going to sample another A into S plus E, where S, E and are two vectors, then you are not able to distinguish between these two. So this is one of the way to say the LWE problem. How you make the adversary harder to distinguish between these two. So if you are able to make the adversary harder these two things, to distinguish between these two result, a matrix A and this As plus E, then you are successful. It means your problem is based on LWE, it is hard, and your communication system is safe. Now the picture of this A and As plus E can be seen in this way. So this is a good way to say the LWE problem, and it is very simple. Like, if you have a linear system of equation, three equations, suppose in case of three equation and three variable, you have written an equation 3x plus y plus z is equal to 7. Similarly, 2x plus 5y plus z is equal to 8. Similarly, third equation. Then you introduce an error in this system of equation. Error, it means error in terms of coefficient. Suppose first equation I have written 3x plus 2y plus 5z is equal to 2. Then you just introduce errors. 3.1x plus 2.1y plus 5.1z is equal to 3. So like this, if you introduce the error, and adversary have to find the solution of original equation. He has the errored equation and he has to find out the solution of original equation. So that must be hard, and because based on the whatever the error you have introduced. So this is the complete picture of the LWE. On that, the algorithm of digital signatures and uh, mm, uh, uh, key encapsulation mechanism has been built. So if you go to the details of the those encryption key encapsulation mechanism algorithm, then they have the crystal fiber. So this figure they finalize, and they are not, they, it means they are taking the coefficient in this range 0 to 3329, coefficient of equations, and each vector is of 256 size. It means each vector length is 256. So these figures are there. I will not go in details, because if you go to the details of those paper, then you are able to find out that how and why they have chosen this figure. Because to build a system of equations with the different vectors of which size, and among which domain we will choose the coefficient. So these are the practical problems, and they will come when you are going to design those algorithms. So in case of Kyber, this is the range of the coefficient, and this is the size of the vector. So how the encryption is happening? So encryption is happening, you just find out a matrix A, a vector B, a message, and your output be B dash and V dash. So your encryption is happening in such a way. This matrix A into S dash is again S dash, E dash, and E double dash. All of these three has been sampled randomly. So your encryption will come in such a way, this B dash and V dash. So you input A, B, M, your output is B dash and V dash. Your decryption is happening in this way. You will find M dash, which will come this. So under mod Q, this will become negligible, and you will find out that your message will come. So these are just equations. Using those linear relations, you are able to identify that how the decryption is happening. So based on the security evaluation of those dilithium and Kyber, they land with three version of dilithium itself they have, and they have finalized three version of Kyber itself based on the size of the key. Suppose if I am telling Kyber 512, it means 512 bit is the size of the key. Similarly, Kyber 768 bit is the size of the key. So See, the broad picture, if you are able to see that RSA 256 and AES 256 were there, where the size length is 256 bits or 128 bits. But here, all of them are greater than that. So, in the process of evaluation of those algorithm, they enhance the efficiency also, or they look after the efficiency also, because no one is going to compromise in terms of efficiency. They are going to move the post quantum safety, but how you compromise the efficiency? Whatever we are doing nowadays, just in seconds, if someone will tell that tomorrow, based on security, it will happen in 2 days, then you will just show your face in such a way that, oh, what is happening? But here the question is, the that's why they have standardized these things, and they choose according to the efficiency of those algorithms also. Now, if you see here, then here the problem is the product of this A into S. I told you A is a matrix, S is a vector. So here the expensive operation is happening is the multiplication of these two vectors, and this algorithm is playing the key role in efficient multiplication of two vectors. So I'm not going to details of these algorithms also, but you must aware about this, that how it is happening and how it is processing those the 256 dimensional vector, and they are efficiently multiplying. So if you are interested to multiply two polynomial f into g under this mod of that polynomial, then you just take number theoretic transformation of that f, number theoretic transformation of that g, multiply pointwise, and take inverse number theoretic transformation of that product, you will get the product of these two things. And it is happening in n log n time. So in any case, you will get efficient product of two polynomial, which will which will not affect actually your computational power in terms of that heavy size of the key. Another product, they have used that Karasuba techniques, which is also a very well known method to do the product. Now, if you want to look that algorithmic design of the Kyber or dilithium, then in dilithium it is a digital signature algorithms. So at first level, you are going to generate public key and secret key. So one section have just the generation of the key, and it is happening through random sampling. So random sampling of the matrix A. So here this arrow means that the random sampling. After the generation of public key and secret key, you are going to sign your message. Your M is there, using your secret key, you signed it. And at next level, you are going to verify that whether this message is coming from the authenticated person, correct person or not. So at third level, you are going to verify that the signer is that on which I am relying or not. So this is the uh, building blocks for the generation of the digital signature. But what I am highlighting here is how you are doing the random sampling. So here, this is another you can say area where the computational power or computational process will play an interesting role. So how you will do the random sampling? So the word random is come in the picture. It means you need some information or some random information. From that you are going to sample the information. It means if you are going to sample A, the matrix A, then your source is some random, and from that randomly looking information you are going to sample the matrix A. So the meaning of randomness in nature is different. The meaning of randomness in classical or in computational aspect is different. So here the idea is to generate uh, a data which looks like uniformly distributed. So if you have uniformly distributed information, then you're not able to distinguish that what is occurring frequently or what is the pattern for that. So in that case, this will help to find out the sampling of the matrix A. So how you doing the random sampling? So you start with random number generator. It means you generate a random number, you generate random numbers, and among that you are going to sample the matrix A. So how you divide the random numbers? So it is this is a picture. It means the random numbers has been majorly divided into two sections. One is the pseudo random number generator, another one is the true random number generator. So pseudo random number generators are basically, if you using some program or some mathematical formula, based on that you find out a level of periodicity, like after this much time it will repeat, then it will come under pseudo random number generator. If you come in case of true random number generator, then you can say like uh, some level of entropy you will choose from the device perspective. What is happening in physically, means some physical phenomena you will use to find out the entropy level, and then from that source you are generating a random somehow numbers. So this is called the true random number generators. So this has been further bifurcation also, like because your physical phenomena is maybe the classical, related to classical physics or related to the quantum physics. So accordingly it has been further divided for the generation of random number. Now the question will come, suppose someone have developed a random number generator either in quantum physics phenomena or classical physics phenomena or some uh, mathematical formula, then how you verify that this doesn't have any pattern, or this is more or less the common thing what we are able to observe in the generated random number. It is not available there, because to sample this matrix A we need those uniformly distributed numbers. So there are well known statistical tests. Using those tests you can easily verify that generated numbers are random. Here the idea of those randomness test is not to verify the source. It is very clear, like all those randomness tests, there are multiple randomness tests. These all tests have based on some statistics. You fix some statistics like generated and random data we have. We find out that whether they are equal number of 1 or equal number of 0 are there or not. So it is a type of pattern, equal number of 0 and equal number of 1. So if it is there, if it is not there, so based on these hypotheses or these statistics, the randomness test has been built on, and using those we can verify that the randomly generated information available in a file is random or not, or you can say they're uniformly distributed or not. So if you see that the Knuth battery, the battery they called it in generic word for all, because they are collection of different statistical tests. So this is a very common statistical test. and in which you can find out 12 different statistics in the generated sequence. NIST is also there in that, and in fact it is a uh, common you can say that collection of statistical tests which are used by industry to verify the randomness of a generated file. So it includes 15 different statistical property. They have verified it, and then they will tell that okay, generated file is random. Similarly, die hard battery test, it has containing 15 statistical property. They will verify it, and then so they are openly available. If anyone is interested to find out the details of those things, then you can easily find out that what type of tests is there and how you verify the, because that is also interesting area to develop a random number generator and verify through those tests whether your whatever you generated is satisfying those statistical property or not. Third one is the ENT entropy test. In short, it is called ENT battery. It has include 5 statistical property. But if you go in depth of those tests, then you can find that you can easily fool those tests also. So 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 actually there are statistical properties, and simply I can say if I'm looking those three number whose average is 5, then those three number is 555 also, and those three number is 532 also, 538 also, 537 also. So that is also, it means how you strengthen those statistics so that you can tell that this generated information is random. So it is keep on going task. Nowadays some other properties has been explored on random information also, based on uh, algebraic properties, based on the boolean characteristic of the properties, and then they are saying that the generated data is random or not. So this bool test is also a common test. It has been proposed recently, and using they are also using statistical property. It means count of some specific patterns in given in generated sequence, and they will tell that oh, this pattern is occurring frequently, so this not looks like a random. Similarly, the script X. So if I conclude in such a way, then you can say that how to build those test of randomness. But in case of random sampling, we need deterministic random number generator. Deterministic, it means I told you earlier in my first slide, the division of cryptography is symmetric, asymmetric, and hash. So hash function were playing a key role in sampling of that matrix A. So if you go in details of those algorithms, then you will find that how they are sampling those vectors inside A, S1, S2, in dilithium as well as in Kyber, because I already told that it is based on lattice based, and lattice are based on vectors. And how they are sampling those vectors? So they are sampling from the uniformly generated random numbers. So how those uniformly generation has been happening? So it is happening through hash. So the hash function is playing the key role in designing of these algorithms. Since hash function is also um, came after so many rounds of review by NIST. So SHA-3, SHA-3, you can say, or K-SHA Keshak is also another name of the SHA-3. So this is the name of those algorithm which are in use to sample this matrix A. And why I am using this, why I am telling the deterministic random number generator. So the SHA-3 is basically used as deterministic random number generator. It means using SHA-3 algorithm, you are able to generate a uniform sampled random number, and from that you are able to sample A, and you start the generation of public key and private key. So this in such a way, but the question is that if you going directly to SHA-3, that is fine. If you are going to some other pseudo random number generator, then you have to verify that and test it that whether it is passing the randomness test or not. So in this way, all of these development has been coupled in the question of the uh, cyber safety of our communication system. So they and these building blocks are designing of the post quantum algorithm, seeing their efficiency, and efficiency relies on the generation of the random sampling, testing of those generated vectors, and fixing the parameters for the algorithm, that what is the length of the vector, what is the size of the coefficient, from which prime number you will choose. So these all verticals has been coupled in such a way, because this is not easy task to mitigate, to migrate the whole available communication system to a new standardized algorithm. We have to go year by year. That's why this 2035 or 2030 has been framed the year, so that they are finding those level of efficiency they are achieving, that whatever we are doing now, the same efficiency we are able to achieve with the proposed algorithm. So this is the case study for those algorithms and how those computation is going on. So you can see the references. First one is that the review paper, and the pqcrystal.org is the website where you can find out the details of those algorithms. Yeah. So I think,
Participants,
yeah,
participants,
any
please post
question
your
if you have.
queries.
Yeah.
You can feel free to ask any question. You can post your queries in chat box, or you can unmute yourself. Participants, you can post your queries in chat box. Sir, I think there are no queries.
Yes, no issue, ma'am. It may happen, like it will take time to.
Yes. Yes.
Yeah, maybe the question will come online, then let me know. I will free to
So there
answer.
is one question. There is one question.
Yeah, 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 sure.
Dr. Asra Sadaf, ma'am, has some question.
Yeah,
Ma'am, you
yeah.
can unmute yourself.
Good evening, sir. Thank you so
Yes,
much,
good
sir,
evening.
for this wonderful session you have taken. And it is a lot of learning from, we are learning a lot from all these sessions which has been organized. My question is, sir, that when we will be teaching these things are to our students, because many of our students are interested in research, getting into research on these topics. So, is there any way that we can provide them some specific topics where they can work upon, or they can do research in during their ME, something like that, I want to ask sir.
If I am getting your question, then you are asking that how you approach to student for those problems, huh?
Correct, correct, sir.
Yeah. So, what I can tell, ma'am, like you just start with some toy examples, and because they are available open source available tools, like whatever the algorithms and whatever the things I am telling, they're open for public. So at least you can tell that to explore and read those things so that they can, because anywhere if I'm looking for those type of students from my perspective as well, then these things I will see in preference that they are at least aware or not. So first scrutiny we will do in such a way itself. So first thing you can do, start awareness, like they should know that what is happening, what is inside, what mathematics is happening there, what physics is happening there, what current technology they are using to enable those technology. So if this is the primal structure, if some student will go beyond that, then you can tell that the student to go in depth for those things, because these things are available in public. They are not like in fact I already told that NIST has initiated in this much year and this much year has been taken to finalize these things. Till 10 year is went gone off, and then finally they finalize. But uh, it means the person who actually want to interest, then they have to see those steps stepwise, that what is happen at initial level. So it is a type of story thing also. If you go through those details, then you can motivate those students through stories also. Like I told you what happened to break that Sikh and Siddh two algorithm. So that primary level, at least they should aware that now we are going to shift towards those new technology, and then they can start like that.
Okay, sir, I will guide my student accordingly then.
Yeah, sure,
Thank
ma'am.
you.
Yeah,
Thank you, sir.
yeah.
Any other participant wants to ask
So,
question?
second problem that arises is when students work in this particular areas. These are very advanced areas, but it so also happens if we try to put the paper in certain journals, they, I mean, openly, as if you take the scope into consideration, there are no journals with this particular area as scope, but you can see the papers are being published in this particular area in the same journal, in spite of they are not listed on the scope. But at certain times when you try to put a paper, then it says ki this is out of scope and it gets rejected. So how do you think this problem can be addressed?
Yeah, ma'am. Actually, there is a fine line between, I can say, the academia thing and industrial. Still, it is there. So, if you see the perspective, you see from the perspective of industry thing, then all of these thing is happening tremendously fast, and people are appreciating who are doing in the industrial development. But if you see those in terms of publishing those results, then 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 you should focus on the specific community. Like if you going for the cryptography, then there is well known International Association of Cryptographic Research, where you can't find the those journals which are listed in terms of theoretical aspects of maths or physics. But the all our cryptographic domains development, either it is happening in industry or academia, both of things are there. So if you see, I request you to see that international IACR, International Association of Cryptographic Research. So they are organizing regularly. In fact, their one of the agenda is there to promote the study of cryptography and cybersecurity related things. So
Okay, I'll
I
see
can
to
suggest
that,
this.
sir.
Yeah, yeah,
But sir, can you give your mail ID as well?
yeah. Sure, ma'am. It was there in the
Yeah.
slide, but you can write like.
Yeah, it was a very informative session. Thus, thank you.
Okay, thank you, ma'am.
Uh, any other question, participants? Okay, sir. I think there are no questions. Um,
Okay.
First and foremost, we extend our heartfelt thanks to Dr. Shashikant Pandey, sir, for his insights into the organization of quantum computer system and the critical aspects of ethics and security in data-driven quantum computing. His